talked about if you were to look at how the electrons are for any of these elements, you would see that they would end in like a what we call NP6. The NS2, NP6. If you take 2 and 6, you get 8. So that's the complete octet. We're talking more about that. I think my next point up here is as we talk about chemical reactions and or probably more specifically how compounds, how like atoms stick together, like in water, you have 2 hydrogens and an oxygen. Why they stick together? It's going to be kind of either share or transfer electrons to get a complete octet. Okay, so we'll be talking about that. Now, all electrons are not created equal. So there are these important electrons called valence electrons. And collectively, the valence electrons together make what's called the valence shell for that atom. Okay? And they are in the highest N. So if I pick on iridium, the highest N, remember N is the number with the subshell. So the highest N, I'm liking 6. It's my highest N. Okay? So this is actually, I only have 2 valence electrons, and here they are. Okay? So it's weird to think, but anything then that's not valence electrons are core electrons. So out of the 77 electrons, 75 of them are core. 2 are valence, and they are in the 6s subshell. Okay, so those are the special guys. Like this says, those will be the ones that kind of come and go or share or whatever. I have an example here. If we pick on silicon, silicon is atomic number 14. So these are cool. This actually 1s2 to 2p6. That's neon. Beyond neon, then we need to go ahead. Beyond 10, we need 14. Sorry, beyond 10, we need 4 more electrons. This is where those other 4 electrons are. So just like I did up here with iridium, if we're looking for the highest N would be 3. So we're looking at these 4 electrons are valence electrons. So here's one for you. If we pick on selenium, beyond argon, so here's argon. So based upon argon, argon would be part of the core electrons. Okay. So beyond argon, as we're finding homes for those, let's see, selenium, 34 electrons, it looks like this. 2 electrons in the 4s, 10 electrons in the 3d, 4 electrons in the 4p. So the highest N is 4. So here we actually have a situation where our valence electrons are kind of between our valence electrons, as we've added them anyway, we have the non-valence electrons. So 3d is part of the core electrons. 6 valence electrons. So this is this arrow diagram, which again, the sheet I gave you says you will draw this for credit on your test on Tuesday. And you can use it. Hopefully you'll draw it correctly so you can use it correctly. Every once in a while I run into students that don't draw it correctly and then use it, and then I have to kind of find them that work. But this is applying the lowest N plus L rule, because we did this the other day. For any subshell, we can come up with an N plus L value. And so with this N plus L is equal to what? 1, 2, 3, each diagonal is a different N plus L value. So this following the arrow diagram works for most elements. There are some exceptions. There's always going to be exceptions. I'm going to kind of show you why the exceptions occur. This is to say that chromium, if you're finding homes for the 24 chromium electrons, they aren't going to follow this. Okay? But I'm here to tell you, anytime you have to do homework or a test question for me, this is what you're going to follow. Okay, so if we pick on chromium, chromium has 24 electrons. And this is how we would write it. Okay, this is in the order of filling. We would come up behind, well, let's see, that would be argon. Yeah, beyond argon, we have 6 more electrons. Okay, yeah, 6 more electrons, and here's where they are. 2 in the 4s and 3 in the 4d. But I'm here to tell you that this is actually what those 24 chromium electrons do. If we look at what moved where, you're going to see that one of these guys moved here. This, instead of having 2, we have 1, and here, instead of having 4, we have 5. One thing in my next slide tells you why this actually happens. It's preferred for chromium. It's a lower energy. And if I take any D-type can accommodate 5 electrons, any D-type can accommodate 10 electrons since it's got 5 orbitals. So half of 10 is 5. So actually, in this case, each electron has its own room. It's nice and happy. Each electron has, or this electron has its own room. So, to put another way, the reason chromium does that, and the reason we find other exceptions in the B elements, these would be the transition, and maybe even intertransition elements, would be to get a half-filled D-type or half-filled F-type, which would be 7. In some cases, you'll see kind of migration of an electron to completely fill the D or the F, which would be D10 or F14. So 24 is chromium, 29 is copper, also another exception. 41, 42, you're looking at these guys right here. Okay, so these are where your exceptions occur, and the previous slide says why they occur. But again, just to make sure we're on the same page, if I ask you on the test, I'm asking you to follow this. Every once in a while, I'll pick something that's an exception, and students will write something else down. Like, well, where did you get that? Oh, you didn't. You probably got that off the internet. Okay, but I want you to apply Rose Episode rule. So let's talk blocks. So you can kind of see the colors: the blue, the kind of brown, the pink, the green down here. So as it turns out, we kind of can call these an S block and a P block. Okay, so S block and P block, they are groups, group 1 and 2, S block, groups 3 through 8, P block. That means that, and you kind of see it on the slide, so you have to look really closely, but as we add electrons, the last electrons to be added here will be S, the last electrons to be added here will be P. And then we have 2 more blocks. This block is the D block, but it's not just the D block. It's what we call N-1 D block, where I think I've played around with this too. This is something new for me. You can actually make this larger, like that. Is that not cool or what? It's the little things, right? So it's D block, but it's N-1. So if we find scandium, I want to say, it's actually in period 4. There we go. So scandium is in period 4. Okay. So here, though, it's N-1, so it's not 4, it's 3. So N-1 D block. So if we're kind of hop, jumping, and skipping, adding electrons, these electrons are going to be added to D, but it's N-1, so it's a period -1. And then the last block would be the F block. But it's not just any F block, it's N-2. Okay. So, for instance, I think I tried to explain this. If we're going through atomic number 55, 56, 57, and then we go 58. So, in other words, the lanthanide series is actually part of period 6. So 6 minus 2 is 4. So here we are actually adding 4F electrons. Okay, now this is where it starts to get a little, this part kind of confuses me. So let me show you how we can use this to our advantage. I'm not going to go iridium, but let's go something easier. Let's go zirconium. Well, we did that one before. Let's go technetium. So here's how this would work. If I want to come up with the 43 electrons associated with a technetium atom. here's how I could use this to my advantage. I would go ahead and write krypton, okay? Right? Some of you guys want to do this, so that's what I would do. In brackets, I'm going to write krypton, and then beyond krypton, I need to account for these electrons. This is how I think of it, and it works pretty good. I need to account for these 2 electrons going through the S block. So it's n is equal to 5, so this would be 5s2. And then I need to count for these electrons going through the D block. How many? 1, 2, 3, 4, 5. Okay? So I need 5 electrons in the D block, but it's n minus 1. So it's 4d5. So I'm going to tactile sort of person. So that's the way you can just at a glance kind of know where you are. So just to recap what I say, krypton, and then I'm jumping through period 5. So my first 2 electrons are going to be 5s. I need both of those. And then I'm going to go 4d, and I only need 5. Okay, so it's a possibility. It's kind of a shortcut way. The problem with it is that, like I said, it gets kind of confusing when I start introducing F-type. I usually have to have them, I kind of do a hybrid method where I have my arrow diagram to kind of confirm that I have this right. Okay. So anyway, one last thing I wanted, oh yeah, so this will be, remember how we did this? So we have the second set. You probably already worked the first 3, and now you need to work the last 4. So one more thing. Yeah, I'm going to hold the part on atomic size until Friday. But I did want to show you this other little bit. I've added a link to Canvas. In addition to think it's cool where you can move the boxes around. And I've also changed my picture several times. Anyway, so we've gone out to this before, this one. But so if we go to P table, that was the one where you can have P stands for periodic. So periodic tables, you can do a different tab. So for instance, we've been spending some time talking about orbitals. I could click on the orbitals tab, and then it's just what we've been talking about. So I could click on, scandium. Isn't that not adorable or what? It shows you where the electrons are, the little arrows up and down, just like we've been talking about. Here's the electron configuration written out, spectroscopic versus box and arrow. It's just a lot of fun. But my other thing is kind of fun too. So if you type in electron configuration calculator, you'll find yourself to this one, and it looks like this. I like this one too. So for instance, if I wanted to know scandium, I could go ahead and solve it maybe. Okay, so down below here, it's giving me all this information about scandium, including, it gave me the most, I don't know how to do what mass number, but it's giving me all sorts of good information, including the electron configuration that we've been talking about. So, and this one's kind of fun. We'll be talking a little bit about how electrons are configured for ions, if something gains electrons or loses electrons. And you can, in this solver calculator, you can go ahead and put that in. So it's fun. Okay, well, that's all I have for today. I'm used to bumping up against the time, but you guys get out early. Anybody have any questions? So we'll do atomic size on Friday, and then Monday, I maybe give you the 3 materials. Okay.
You said the quiz is on Tuesday, right?
Yes.
Okay.
And we're going to be in that same room in 5 minutes.
All right.